Hello, this is a short video that introduces the notion of instruction pipelining. So in the previous lectures, we have looked at and discussed about single cycle CPU and multi-cycle CPU. And we have also looked at some of the issues that we are facing with those designs. So in this lecture, we'll jump into a new design called pipeline design. So just a quick recap, if we correlate our single cycle CPU with the COVID-19 vaccination schedule that is happening in the country, so there are various steps that an individual has to go through to get the final vaccine certificate. Each stage or step has a different delay or processing time. So if we look at the entire sequence of events, the throughput comes around 1 hour per person, right? So it's a single cycle design where every instruction take one cycle, but the cycle length is it's kind of determined by the longest instruction, right? Then if we just extrapolate, the throughput will be like in 3 hours, you will be done with 3%, right? So it's pretty slow. That's why we moved into the notion of multi-cycle, where the cycle length becomes better. There is no need of a longer cycle, but now you have to spend multiple cycles for a particular instruction, and the number of cycles that an instruction spend can vary. So for example, in this case, let's assume that we have to eventually book 4 slots to get our vaccination done instead of just 1 slot. Okay, so that's the notion of multi-cycle. So with the pipeline schedule, what happens is we try to kind of divide the entire step into multiple sub-steps, ideally independent. Okay, so that there won't be delay. And what we try to do is we try to improve the throughput of the processor. So let's understand what I meant by throughput. So in the pipeline schedule, what you can assume is when the first individual enters stage 1, let's say this is person 1, it takes around 15 minutes to complete stage 1. Then person 1 moves to stage 2, person 2 enters, okay, and like that it continues, right? So now 3 individuals are there inside the processor, okay, or 3 individuals are already part of the vaccination schedule, right? So this goes on. So finally, if you look at the end of stage 5, now there are multiple individuals who are actually in the process of getting the vaccination certificate. They are at the different stages. And if we look at the throughput now, it will be around 3% per hour. Okay. So let's try to understand from where this number comes. So far we have discussed about the notion of worst case latency or worst case processing time, right? So if we assume that and create our pipeline schedule where each stage is taking a fixed latency and 20 minutes. This 20 minutes come from the previous stage 4, which is the worst case stage. Okay, there is no stage that takes more than 20 minutes. So if we assume all the stages are taking 20 minutes, right? What you can realize is suddenly the latency has gone up to 100 minutes. So previously, one person can be done with the vaccination in 60 minutes. Now the person has to spend 100 minutes, right? But if you look at the throughput after initial hiccups, you'll see that every 20 minutes, one individual is getting done, right? Which means the throughput is 3% per hour, right? The first time when the individual enters into this different stages of pipeline schedule, he or she has to go through all the stages and eventually it will take 100 minutes. But after that, all the rest of the individuals will take additional 20 minutes, right? Because all the stages are of equal size. So this way we are kind of improving the throughput, right? So one subtle point here, why fixing all stages with a constant latency, delay or processing time? Well, that there is no requirement as such. This is just a 101 level introduction to pipelining. So because we have understood the notion of worst case latency, so this is just an example that tries to create a pipeline schedule where all the stages are taking same amount of time. But you can actually go for variable stages and try to calculate the latency and throughput, see whether it improves or degrades. So let's pause a bit and understand what we have seen so far. In the single cycle design, the cycle time is long. Remember the 8 nanosecond example. CPI is 1 because 1 instruction per cycle. Okay. Then we move to multi-cycle. The cycle time becomes shorter. So we move to 2 nanosecond cycles. But in the process, the CPI is greater than 1. So if you remember, now it will take around 4 cycles, let's say. Right. So with the pipeline design, the cycle time is still short. Let's assume 2 nanosecond. And the CPI is still 1 because after the initial, out of the first instruction, all the rest of the instruction will be, done in 1 cycle. So it provides you CPI of 1 and the cycle time is still short. So this is the best of both the worlds. That's what we are looking for, right? And the key here to, kind of remember and understand and appreciate is that pipelining improves throughput. It doesn't improve latency. It may increase your latency or it will increase your latency depending on your design. Okay. So just a historical context, if you want to get into the notion of pipelining and how it came to computing, go and look at this video specifically up to 1 minute 25 seconds to kind of get a connection between pipelining and Richard Feynman. So with that, I will stop here and thank you.